Log on, tune in, find out. Another good idea from Cambridge.
It's my pleasure to welcome Patrick Fayard, and he's going to talk about geometrical implications of the compound representation for weakly scattered amplitudes.
Good morning. Good morning, everyone. First, I would like to say that I'm very pleased to be here. This gave me a chance to listen to many interesting talks. And now I will be able to discuss some works I did with my doctoral advisor at McMaster University in Field. So actually what we did, we considered a very specific scattering problem, and we used an approach based on probability theory to solve that problem. So to give you some sort of background, the amplitude scattered from a roof, for example from the sea surface, usually is made of two components, as a product of two components that are known in the radar community as a texture on the speckle. And if I'm here today, it's because it's kind of an inverse scattering problem. You have your scattered amplitude and you want to extract the texture from it. And a way to do that is to work in a stochastic framework using E2 calculus that enable you to derive the dynamics of your scattered amplitude, and then from those dynamics derive some interesting results. So this work was done was motivated by radar application, especially high resolution radars, when the speckle is an issue. But interestingly, the mathematical formalisms we have been using can also be relevant to some specific nuclear magnetic resonance application. And basically you can draw an analogy between the scatterers you get in your radar beam with the number of spin you have in your NMR sample. So I mentioned about E2 calculus. So for those of you who are not familiar with it, let me just say a few words. First, you have to introduce the Wiener processes, which are defined by their three properties. First, their initial value is 0. Then, non-overlapping increments are independent. And finally, those increments are normally distributed. This enables you to define the E2 integral, or that is equivalent to the E2 stochastic differential equation, in terms of a drift, B, and a volatility coefficient. So basically the idea here is that that term is of order delta t, while this term is of order delta t square. Or in other words, you want to consider positive quadratic variance. On this, also in this E2 calculus framework, you have a set of formula. For example, you have a formula that gives you the derivative of a product. So what is interesting is that you have the usual term u prime v plus u v prime, but you also have the product of your two derivatives. So this is relative to the fact that you are considering the quadratic variance. And also, many of you might be familiar with the Fokker-Planck equation, and there is actually an equivalence between the E2 integral for your process and the Fokker-Planck equation of its probability distribution. So our first step is to assume that the scattered amplitude you get can be written as the summation of n scatterers' contribution. So in practice, you have your radar beam, and you are assuming that within your radar beam you will have a few objects that will reflect your incident wave. And this is called strong scattering, so you are writing your scattered amplitude, epsilon, as a summation of n phasors. All of these phasors are normalized, and they have independent phases that are uniformly distributed in the interval 0 to pi. So what you do next, you are making the assumption that those phases phi of G can be written as a collection of displaced linear processes. So I think that phi is a pure linear process. And then, if you use Ito formula, you obtain the following stochastic differential equation for your scattered amplitude, where B is basically related to the time scale of the phase linear process. What is very interesting with that formula is that it gives you the dynamics of your scattered amplitude. And you can think that you have the usual term of the ordinary differential equation plus some noise, some sort of noise term. And this enables you at any time to know the evolution of your scattered amplitude. So in that figure, I'm trying to show what you are doing, what you are actually doing. So in red, I have plotted the scattered amplitude. And what you do is that you're writing it as a summation of n. Here, n is equal to 7 or 8, I think, of n phasors. So here, you have your first phasor, your first component, second one, and so forth. And as you can see, all of them are normalized, and their phases are uniformly distributed. So next, another very important point is that scattered amplitude has a multiplicative nature. As I said, it can be written as a product of a speckle multiplied by a texture. And actually what happened is that in the 80s, when radar engineers started to use high resolution radars, they observed that in the scattering data, there are two components of very different time scales. They had some very slowly varying, some rapidly varying component, the speckle, and some more slowly varying component, the texture. And what is nice is that you can derive this compound representation from your random walk model. Oh, sorry, I forgot to say that this representation is called the random walk model. So from that random walk model, for a large population of scatterer, you can derive very useful component representation. So basically you do two things. First, you consider the normalized scattered amplitude psi of t, and then somehow you are considering separately the time evolution of the number of steps in your random walk, and that term is is more or less the scattered amplitude you get from a constant number of steps. And this is what is called strong scattering. So basically you are writing psi of t in terms of a speckle gamma t modulated by the square root of a texture xt. And those two processes are independent. They are independent because basically gamma t is of electromagnetic origin. It tells you how your incident wave is reflected depending on its incidence and so forth. Whereas x of t has to do with the geometry of your problem, namely on how rough your surface is, for example. So the speckle gamma t, you can show that it is an Einstein dynamic process that is characterized by this stochastic differential equation. And here you have a constant b. So the inverse of b is a characteristic autocorrelation time of your process. And in practice for radar application, b minus 1 is the order of milliseconds. And it's basically connected to the wave number of your incident wave. Next, you have the texture x of t. And you can think of x of t as being the local power of your scattered wave. And there is a very common situation for radar application that is called k-scattering. In that case, x of t has a gamma distribution. So if x of t has a gamma distribution, you can characterize it by the following SDE. And here your characterizing time is much larger. It is in the order of seconds. And I should also mention that that stochastic differential equation is derived from the Fourier-Planck equation for the associated probability distribution. If you are assuming that the number of steps nt follows a birth-death immigration model. So originally I was intending to draw a cartoon to give you a crude understanding of what happens. But during my high school days, I used to fail most of my art classes, so I decided to use someone else's work. Just to give you a crude understanding of what is happening. So this is a painting from a 19th century Japanese artist. Correct me if I'm wrong, but I think that his name is Rutsai. So basically, what I want to explain is that you have two different structures in your wave. You have those sort of long. I'm speaking in terms of spatial time scale, spatial length. You have this kind of very long texture. You have this kind of texture. So the waves, you can think of it as having those components that you call a texture that are very slowly varying. And then you have this much more rapidly varying small things that correspond more or less to your speckle. And so this gives you a crude understanding why you want to have that component representation of your scattered amplitude in terms of a texture on a speckle. Because if with your radar you want to detect that boat, the speckle will be some sort of noise that will prevent you from detecting it. In other words, it's much easier to detect an anomaly in the texture than to detect an anomaly in the scattered amplitude. This is why you want to extract the texture from your scattered amplitude. And here I have a first intermediate result that tells you that the texture x of t can be expressed in terms of scattered intensity zt multiplied by the squared phase fluctuation delta theta squared. So what this means is that once you get your scattering data for the scattered amplitude, which is a complex process, you can just take its square modulus for the intensity, and then use the fluctuation of its phase, and combining those two gives you an estimate of your hidden texture x of t. And something important to keep in mind is that you can show that your scattered amplitude in this case the angular and radial fluctuations of scattered amplitude they correlate. Here I have a slide that shows a quick comparison with Kalman filtering. So with the previous formula, we have a way to infer the exact values of the underlying signal x of t. And you can think of, and it's very reminiscent of the Kalman filter because you have your hidden state x of t and you observed state the intensity z of t. And for each of them, you have a stochastic differential equation. So if I'm using the terminology associated with Kalman filtering, here you have kind of your state update equation, and here you have your noise. Whereas here you have the mapping from your observed state to your hidden state, and something, some noise. And so, with the previous formula, we have a way to solve this system of equations to extract x of t. So that previous result was derived for the so-called strong scattering. But there is another very interesting experimental situation where the scattered amplitude you receive, uppercase psi, can be written as your strongly scattered amplitude lowercase psi plus an additional covariant offset. A bit earlier I spoke of the random walk. And you can think of this weakly scattering case as if you had a bias in your random walk. And now it is the same thing. Given that equation, you want to find a way to extract the texture x of t. So to do that, first you have to introduce the polar representation of your scattered amplitude. Then what you do, you consider the fluctuations of your weakly scattered amplitude psi. So here I'm just considering the volatility terms. So it is made of two components. This is related to your phase fluctuations, and this one to your radial fluctuations. And you can show that for a weakly scattered amplitude, the radial and phase fluctuations are correlated. Whereas for a strongly scattered amplitude, this is not the case. So this motivates you to do something kind of interesting. You introduce a dyad of angle phi, with respect to which the weakly scattered amplitude component fluctuations decorrelate. So now you can write your amplitude fluctuations in that way, in terms of two processes alpha t and beta t that are independent. And you can do that by introducing this angle phi of t. This idea is a little bit, is not that much obvious. So I have a graph that represents what is happening. So here, this is your strongly scattered amplitude lowercase psi that is shown in the complex plane with its phase theta t on its magnitude RT. So you can show that for a strongly scattered amplitude, the radial fluctuation in that direction and the angular fluctuation in that direction, they correlate. Next, we move to the weakly scattering case, weak scattering case, where you have your weakly scattered amplitude uppercase psi. It is written in terms of a current offset E of t plus your strongly scattered amplitude lowercase psi. But now, if you consider the fluctuations along that direction, they are correlated with the fluctuations along this direction. This is why you introduce a dyad such that here you define two new fluctuations components that are independent. So as we are working in an Ito calculus framework, we can derive the Ito differentials for the intensity and for the phase as follows. If you do a little bit of math, you find the following expression for the Ito differential of the phase to the first order. It is expressed in terms of two linear processes. This linear process is associated with a cross section, and that one is associated with a speckle. If you do a bit more math, you can obtain the following formula. Here in that formula, sigma t sigma is the squared phase fluctuations d theta t over dt, where this is the cross volatility between your intensity and your phase. So what that formula tells you is that the x of t, the texture, is observable through the intensity weighted squared phase fluctuation minus the cross volatility weighted by the tangent of the phase rotation phi of t. In other words, you have your hidden set x of t expressed in terms of four quantities zt, sigma t, sigma t, z, theta, and tangent phi, in terms of four quantities that are directly observable from your scattering data. And I don't know if you remember the previous formula I gave for strong scattering, but for strong scattering, the radial and angular fluctuations decorrelate, so you don't have this term. This term accounts for the correlation between your radial and angular fluctuations in this weak scattering case. One more thing is that, interestingly, you have a component result where you can express the texture x of t in terms of sigma t z here. So one more time, you have two different ways to obtain in local time the texture from your scattering data time series. So what you do in practice with discretely sampled data, you can write that formula. Actually, that gives you an estimate for your state x, that gives you an estimate of your texture at time I in terms of those four quantities being directly observable from scattering data. And so what you do next, you have to apply a smoothing average to the left-hand side here to obtain an estimate of your state xi. So here I have a figure to explain what you do. I have done some simulations to explain how you proceed. So first you have the blue curve that I obtained by solving numerically the cross-section, the texture stochastic differential equation. Once I have the blue curve, I can generate synthetic scattering data. For example, in black, I have displayed the scattering intensity. And as I said, so you are starting, this is your starting point. You can generate synthetically scattering data, and then you can use the previous formula to infer the red curve. So of course the red curve is only obtained from your scattering data. You are not using directly the blue curve. So as you can see, this gives you a very accurate, usually the correction coefficient is greater than 0.95. This gives you a very accurate estimate for your hidden state x of t. And actually you can go a little bit further. You can even quantify the accuracy of your inference process. So you can show that you have that when you are inferring your cross-section, you are making the following mistake, where delta t is your most important parameter and is the number of samples over which you are smoothing your state estimate. So then it's very easy to derive a condition on delta to minimize your smoothing error. And basically what you are doing, you are deriving an analytical expression for your smoothing error in terms of its two asymptotic behavior. As you can see, this analytical expression is quite accurate. It matches quite well with experimental data. And then this gives you a condition on the number of samples over which you should average your state estimate. So here is my conclusion. So basically the problem you are considering is the following one. You observed a weakly scattered amplitude psi of t that is defined as a function of your state, xt, plus that strong scattering amplitude. And what is important is that x of t is arbitrary. It can be any function of your state. And next, you are not making any assumption concerning x of t. As long as it is a neutral process, the results I derive are valid. So this gives you a very broad range of experimental situations that are covered by this equation. So what we did, first we are working in an ito-calculus framework, and then we introduced a dyad to decorate the component fluctuation of the scattered amplitude. And then, by using the geometrical properties of the component representation, we derived an algorithm to infer xt in local time from scattering data. And that local time thing is kind of interesting because you can, in real time, obtain an estimate for your texture in terms of your scattering data. Thank you for your attention.
Questions?
Well, is there a dependence on the wavelength of your radar? Is that in the E?
I would say that it is more or less related to the gamma term. Yeah, but if you want, for example, a way to think of it is that you can have some sort of multipath. The amplitude you get can be written as in terms of multipath integral, right? You have different components. And in that case, this multipath term will be accounted for by that E function.
Does the wavelength enter someplace else? Or?
It probably, we didn't really study that, but it probably does in terms of your stochastic function, in terms of the parameters you have to plug in there.
Yes.
Is there any sense of ill-posters where you have to do some regularization, and if yes, how do you do it?
What do you mean? What do you mean? What do you want to read?
There's somewhat inverse problem behind what you're doing, so there might be something ill-post. So do you have to regularize somehow? So do you feel an ill-posters when you do the numerics?
No, not really. As I said, it's kind of a very broad situation. You can, no, not really.
Can I just ask, so this assumption that xt is an Ito process, I don't really have a feeling for it. How reasonable is that physically as a model?
Actually, what is interesting is that, for example, even if x of t is non-stationary, then this formula will work.
Any questions? No more questions or comments? I'll thank the speaker again. Thank you.